Hello everybody. My name's Steven. I work at LinkedIn as an engineer. I'm going to be talking today about building Python with Gradle. And so we have a nice small group right here. And I was interested, what are we? Are we Python developers? Are we Gradle developers? Show of hands, who uses Python, who codes in Python? Okay, I'm assuming the rest of us, we manage build systems that maybe are powered by Gradle. Do we build any other languages that aren't Java with Gradle? Okay, like what? Ruby? JavaScript? JavaScript? Okay. I'm going to punish you all then by sharing some deep, gory details about Python with you. But in the end, we'll be able to maybe wrap it around and show you how you can apply some of the things that I'm going to talk about today to other languages out there, JavaScript included. So I've worked at LinkedIn for 4 years. During that time, I've worked exclusively with Python. Right now, I'm leading a team called our Python Foundation team, and we maintain basically Python as a platform at LinkedIn. So we do everything from manage our core libraries to security, lots of other things. During that time, though, I think that the most challenging thing that we've had to deal with is dependency management and building in Python. So today I'm going to really discuss why that's the case. I'm going to talk about why build and dependency management is particularly hard in Python. What do build systems today look like for Python? And then lastly, what we can do today, right now, to build better build systems with Python. So anytime, and this is where the punishment begins, anytime we want to talk about Python and package management, we have to talk about setuptools. So setuptools is this de facto package manager for Python. It facilitates packaging, module definitions, distribution metadata, installation, platform-specific details. So I mean, it compiles C and C++, and it does lots and lots more. It also has a pretty interesting history. Over the years, it's diverged into several other projects. And so first came distribute, then came setuptools, then came distutils, then a fork called distutils2 came, and then setuptools came back. And now they've all converged back into setuptools. And so it's a pretty interesting history, pretty complicated. And there's some pretty interesting content on the internet about its evolution. So simply put, setuptools to Python is everything. It's the de facto standard. All Python packages today use setuptools or a flavor of it, as I described, distutils, distutils2, whatever. And so setuptools, and specifically its interface, the setup.py file, that thing I just showed you, it has the ability to become incredibly complex. If you look at this, this is evaluated Python code. And so that allows us as engineers to find an infinite number of ways to solve our problems. It's also an API. So setuptools exposes a programmatic API. And again, the possibilities with this API are endless. So then over the next few slides, I'm going to talk about how people have used this API to build their build systems or tools to help them power their build systems. And we'll start with virtualenv and pip. So these are two tools that are built atop setuptools. I'll start with virtualenv. It's a command line tool. You use it to create environments. Right, so you notice from the slide here that I use a command line program to create this thing. It's an arbitrary string, myenv. And in doing so, it creates this Python environment for me. I can activate it. I can run Python. I can deactivate it. Thing to call out here is that the Python that I get when I activate this environment is specific to that virtual environment. You can also see that I have a specific site packages directory. And this is where I would install libraries or dependencies if I had them. This virtual environment is isolated. And it, again, is used for creating these environments. It's really a solution to solve the dependency inversion problem. And this is important for some super developer that has 2 or 3 or 100 products checked out simultaneously and wants to develop and work in them simultaneously. So what's more is to think about the likeliness that those 100 products share the same dependencies or the same versions and that they're all compatible. It's probably not the case, and that's why this virtualenv tool is so important. It allows us to create isolated environments. And virtualenv is that complete solution. Pip goes hand in hand with virtual environment. It's a command line tool that's used for finding and installing the dependencies into these virtual environments. And it, like virtualenv, is just an implementation of the setuptools interface. So you'll notice here, from an activated virtual environment, I can do things like install packages. It does things like searching, downloading. It'll use setuptools, actually do the install. And it apparently says it does cleaning, which I'm skeptical of. But at this point, using virtualenv and pip, we can actually do a micro build, right? We can activate our environment, or rather we can create and activate our isolated environment. We can install a dependency into it. And then once it's installed, we can invoke Python and use that dependency. And so that's a micro build. We've solved that problem. The next step would be packaging, right? How do we do Python packaging? And again, these are going to be using tools that we've already talked about. Setuptools, pip, pex is another one. What's important to call out here is that these tools, whatever they might be, are kind of designed for the job. Setuptools does package management and installation. Pip does installation. Pex does something else. And so think of it as yet another tool that you can use to solve a particular problem. And in this case, it's source distributions, binary distributions, deployable distributions. It's the complement or the next step. After you have a build, you want to package something, right, to share it with other people. So we've covered build, we've covered packaging. We also want to talk about metadata. And so metadata to me is something that helps me reason about my dependencies or my build or my product. Setuptools doesn't provide great ways for us to do this. Right, so there's no way for me to reason about a build before and after it happens, or rather it's pretty tedious for me to do that. And there's no way for me to reason about artifacts after they've been built, after they've been packaged programmatically. And so this is typically the fault of setuptools, and mostly the fact that the interface to the product, the setup.py file, is evaluated Python code. It comes with a whole bag of problems. It's also really tedious to navigate an already built virtual environment because it's going to involve that I go and inspect the virtualenv and look through the site packages directory, maybe using pip or package resources. So it might look something like this. But notice, for example, in this particular example, that I already have an activated virtual environment. That means I already have my dependencies installed, and so I have a kind of chicken and egg problem here. It's kind of a pain in the butt to figure out what did I install. I have to know what to install to figure out what I have installed. And at the same time, there's no way for me to solve larger problems like, what does my dependency tree look like? Notice pip freeze only gives me a flat list. I don't have a tree of my dependencies unless I want to go through and manually assemble that tree by inspecting the virtualenv. So that's a pain. So we've covered build, we've covered packaging, I've complained about metadata, and now let's talk about dependencies. How do I actually declare dependencies? And like everything else with Python, you're going to use the setup.py file, or setuptools. Setuptools has a kwarg, as we call them. It's a keyword argument. Install requires. It takes a list of dependencies, and it also has this syntactic sugar that lets me specify that I want a particular version or range of versions. It also lets me pin versions or just leave them floating in general. It's pretty nice. I can do my job that way. Straightforward. Again, it requires evaluating the setup.py file, and this further complicates that whole chicken and egg problem that I said we have when we were trying to inspect our virtualenv for metadata. Pip took a step in the right direction, and they moved all of the dependencies out of the setup.py into a separate file, but it still doesn't solve those larger problems. How do I get a non-flat dependency tree? How do I calculate my transitive dependencies, and so on and so forth? It also has this nasty habit of introducing new formats. So pip has its own formats that you can't include in setup.py directly, and what you'll find is that people will, in their setup.py file, open these requirements files and then just inject their dependencies that way. They have to do some filtering. Hopefully you get it right. It's a pain. And so setup tools and by extension pip suffer from a really, really, really bad problem. And that's that we actually don't have a dependency resolver. And this issue has been open since, I think, June of 2013. It makes me look like this at work. It's a bad problem. We don't have a dependency resolver. And we'll discuss what that actually means in the next few slides. Now, the root of the problem is that package resources, one of our core libraries that setuptools uses, is greedy. It makes a greedy decision when selecting versions or dependencies to install. That's catastrophic at scale. It can cause big issues for Python teams as they grow. And one of the only solutions that we've found at LinkedIn is to ask our developers to just pin all of their dependencies. This, too, has catastrophic implications, especially at scale when that product maybe releases versions many times a day. So, think, are you going to ask your developers to upgrade their dependencies? When they have them pinned, they know they're working. It's not going to happen. They're going to pin, and they're going to leave it, and we suffer from code rot. And so we have to pick our poison. On one hand, we could leave all of our versions floating or leave them scoped, and we can suffer at scale these things called version conflicts. Is when we can't really resolve the dependency tree for you because we don't have a dependency resolver. On the other hand, you could ask your developers to pin all of their dependencies, and then when they upgrade, if they upgrade, they suffer from these distribution not founds because maybe a transitive dependency was removed or introduced in that release. And so I work on a project called PyOpenSSL. It's a wrapper for SSL that we use in Python land. And we don't suffer from the same problems that we do, like with the products that we do at LinkedIn, right? And I ask myself why. It's because our dependency trees are really simple. I can reason about that in my head. When I see an error, I know exactly what to fix because I only have 2 dependencies, and one of them's a compatibility layer library. So I really only have 1 dependency that I have to worry about. And this is a sophisticated project. Other libraries out there in the world right now, that for Python at least, they typically look like that. It's really easy for us to reason about. And so it's simple. I don't need a dependency resolver. And Python doesn't provide one, and I don't even notice. They also don't iterate as quickly as we do at a company, an internal company. PyOpenSSL might cut a few new versions a year. LinkedIn on the tools team might cut 10 versions a day. And so we need to, or rather, we have very different spaces, right? Our dependency trees are more complex. They have thousands of edges. We iterate very quickly, so there's even more edges. And when you start to think about your dependency trees in this light, and you have to deal with the problems that the dependency resolver raises, you can maybe understand how it might cause issues for a platform team that's running Python. And so when your dependency trees start looking like this, and your customers start talking about your dependency trees, like illustrations from these books, then we kind of have a problem. And so I want to stop here because I'm not ripping on Python. I love Python. And I want to extend a thanks to the Python Packaging Authority and Donald Stuff, who's working on that team, because they're aware of these problems and they're fixing them. And that Python is rapidly changing for the better. I can expect Python 3 to have a lot of these things hopefully fixed. But the fact is we have a problem now, and we need to find tools to fix them now. And so to recap, these are the things we've talked about. Talked about the ecosystem, right? We have a whole bunch of tools. We've got a big toolbox that lets us do a lot of stuff. We have a great build system. virtualenv and pip do exactly what I need. Packaging is great. I can do source distributions. I can do binary distributions. I can even do deployable distributions, which is a new thing in Python. The metadata is OK. I can do what I want, but it's painful or hacky. Involves string parsing. That sucks. And then the dependency management world in Python is just downright bad. It doesn't work. And so I think the real limitation nowadays that we have to scale out Python-based products or platforms like my team runs is how do we provide a build system for you? How can I give you a build system that lets you iterate at your own pace as fast as you want? It could be a few times a day, or rather a few times a year, or it could be a few times a day. You know, how do I solve that problem? I think, again, the answer is just to build better build systems. And so I'm going to transition from talking about all of these tools that I've talked about to how I can use those tools, right? How do I use virtualenv and setuptools and pip and pex to build a build system? What do build systems even look like for Python? Because it's certainly not just, you know, package a virtualenv and install some things into it and you're done. It's a lot more than that. And so we can talk about how we can use our tools to, you know, power a build system. And I think one of the most important tools is pip. And it's really great because pip is very polite. It allows me to turn things on, turn things off, enhance things, remove things, and it allows me to solve my problem my way. Now, what does that mean will become more apparent in the next few slides. And I think it would be easiest if we just build a build system in Python real quick. And so this is a very trivial build system. I'm going to write it in Bash. Does anyone have a build system at their company written in Bash? Oh, well, I'm going to show you how to fix it. Well, this is pretty simple. You create a virtual environment, you activate it, you install your project into it, you test it, and you package a source distribution, right? Works, but it suffers from all of the same problems that we just talked about. It's using setuptools dependency resolver, and this will not scale. If you're really cool, you probably are using wheels, but again, it's still using setuptools under the hood. It will not scale out. The natural next step then is to use some of those polite features of pip and disable that part of Python that it admittedly is not doing well in. And that means turning off pip's dependency resolver. And pip, by extension, means setuptools. So just turning off the dependency resolver altogether and installing everything with the no deps flag. That is a straightforward argument that just says don't install any of your dependencies when I install you. So that's pretty sweet. We've made a huge improvement to our build system, right? The question now is who warmed the cache, right? If I'm not installing any of my dependencies, I'm going to need to have a complete list of my dependencies, transitives included, in this cache directory. And there's a few approaches that we can take here. You know, we could include an entire mirror of PyPy to the repository. No, that won't work because package resources is greedy. We could do the dependency resolution ourselves. That won't scale out of this small project like PyOpenSSL that only has 1 or 2 dependencies. We could build tooling, right, to resolve all the dependencies for us, but that's really tricky, and so let's just use Gradle for that. Gradle's really good at this, and so we're going to just use Gradle to maintain that cache. Have it resolve all of our dependencies, put them into a cache directory, and we'll have pip and setuptools do all of the stuff that it's really good at, which is installation, package management, environment management, and so we can just use Gradle for the part it's good at, and everything else we can let Python do. And with that, I think it's really important to, you know, call out that philosophy, especially with Gradle build systems that want to shell out to the underlying tools to do the actual build, the domain-specific stuff. I really like this slide because I'm a Python developer, and you aren't. And so nobody in their right mind would actually write their build system in Bash, and so we're going to use Gradle for that too. We're going to build a task dependency tree with Gradle, right? That's exactly what you use Gradle for. So first, you know, what this thing does is it resolves dependencies, it runs my build, being careful to always pass in no deps because Python sucks at dependency management. It'll run package using setuptools because it's really good at that. And then last, it'll run publish. Maybe it uploads it to your internal repo and creates the metadata that you need. This has a number of advantages, especially for a company that's already using Gradle. At LinkedIn, a typical plugin looks like this. It's dumb as rock simple, right? And you have to ask yourself why. It's because Python's so good at doing most of the stuff itself. I don't need Gradle to do very much for me. I need it to resolve my dependencies. This package is a source distribution. This package is a PEX distribution. All I had to do is apply a different plugin. And so two notable things to call out with using Gradle with my Python systems are the things that you can't do and you have to fix out of the box. So one, you have to figure out how to represent artifacts and dependencies in a way that Gradle can understand. I think for the most part that means using Ivy. You also might want to integrate with existing metadata systems. So if you have your product's name and version in some JSON file and you want to load that into setuptools, how do you do that? First, let's talk about representing dependencies. We use Ivy. It was a natural fit for us. Source distributions fit very nicely into this pattern. But other mappings, other mappings between Python land and Ivy land don't fit quite so nicely. So eggs, wheels, they don't fit so nicely into Ivy. And what we found, one, we don't use wheels, or we don't use eggs any longer, but we have investigated wheels. And so you kind of have to hack an Ivy classifier to use wheels. And even after you do these hacks, you still have some annoying problems. Wheels use dashes where Ivy might use underscores or vice versa, and that's really hard to unify. And you have to find a way to hack those classifiers and those names to make that work. It's possible, but it's painful. And so I would call out that I hope to see solutions for this in the future. Ivy's not great at doing this, and we have to work around these rocky areas. You also might be asking the question of well, where did I get all of this for my open source dependencies, right? This is all fine and dandy for an internal dependency or an internal product that I maintain, but how did I generate this for, say, request or PyOpenSSL? And the answer is that you have to maintain an internal cheese shop, which is a PyPy repository. You have to build this Ivy metadata somehow, and this largely goes back to representing metadata in Python. It sucks. It's really hard, but it's not impossible. If you can build the metadata once, you can upload it into your internal repository, and you're done. We've built tooling to do this for us because we found it was really painful, and it's tricky to get exactly right, but it is possible. We've thought about introducing distribution classes, and I'll get to that later, but this is something that you will just have to do and deal with. For our internal products, like I said, it's really easy to omit this metadata. It's really the open source projects and dependencies that you really have to struggle with. And by virtue of us not being able to enhance that existing metadata on open source PyPy, you have to run an internal PyPy. That's not a big deal for big companies, especially if you have any sort of legal restrictions on what libraries you are and are not allowed to use. This is probably something that you can fit into your existing workflow already. So although in the example that I brought up now, I didn't show you an existing metadata system. I'm talking about representing your product names or versions or dependencies or specification files outside of the setup.py file. Say you have a Java or a JSON file that has all of that information in it. How do you get the information that's in the JSON file into your setup.py file so that things like sdist and wheels still work when you package them? How can you make sure that your data or your information is passed on to Python to do the packaging? And the answer is to use a distribution class. Using this distribution class, you can write a very simple Python class to implement this. Now, although it's very convenient, I have to warn you, using a distribution class introduces a distribution bootstrapping problem. So you'll have to find a way to solve this if you go down this route. LinkedIn has, but it's easy for us to solve because we control all of the Gradle plugins. So it's a problem because remember, this thing is evaluated Python code. And so as you introduce these distribution classes, you need to ensure now that you have your distribution classes installed even before you can evaluate this file. Again, it's a chicken and egg problem. You have to ask yourself, who's creating my virtual environment and who's ensuring that my distribution classes are installed before I ever try to evaluate my setup.py files. You also can't do this for open source dependencies. For the same reason we can't enhance projects with IV metadata. You can't change them once they're published. Egg has the right file contents. It has the .sos or whatever your platform needs. but it doesn't have the metadata, and so it's really hard to reason, again, with metadata discovery, like what the hell is this egg? Does it have Linux stuff? Does it have OS X stuff? Wheel addresses that by inlining all of that information directly in the artifact name. And so that's why we've moved to wheels. It's also the way forward in the Python community. And so just by virtue of trying to keep up with open source and making sure we're using the latest and greatest tools, did we choose to abandon egg and go with pip's wheel. So we got 2 happy LinkedIn Python developers here. Thank you guys for coming. Yeah.